I spent 3 weeks fine-tuning my own LLM model, built the database, burned through GPU hours, saw the loss curve go down. Everything textbook perfect. Then I tested my fine-tuned model against the base model, and the base model won without even a single second of training. And honestly, that was the most valuable lesson of my AI journey. Today, I'm going to tell you everything I wish someone had told me on day one. What fine-tuning actually is, when you should do it, when you should absolutely not do it, and how you can fine-tune your own model on a free Colab GPU. So let's go. The plan is simple. We need only 5 things. Number 1, the correct mental model for fine-tuning. Number 2, hardware and tools, meaning how you can train your own model without burning through a monster GPU. Number 3, the dataset, which is a real game. Number 4, training and only the settings that matters. And number 5, evaluation, the thing 90% people skip and which saved me from public embarrassment. By the end, you will have a complete roadmap. There are screenshot-worthy moments coming up, so stay ready. Mental model first, because this is the place where people go wrong. A base model, Llama, Gemma, Quen, whatever, is like a fresh medical graduate. They know a bit of everything. Fine-tuning is sending that doctor to a specialization, let's say making them a radiologist. Now, they'll read an X-ray better than a general physician. But notice something, they didn't relearn medicine. We specialize their behavior. Remember this line, fine-tuning changes a model's format, style, and domain behavior. It is not a reliable way to inject new knowledge. For knowledge, you use RAG. Bring the documents to the model. Don't make it memorize them. So, when do you fine-tune and when do you not? I ask myself these 3 questions on every project. Question number 1, can a well-written prompt can get the job done? If yes, then don't fine-tune. Prompt engineering is free, fine-tuning is not. Question number 2, is the problem about knowledge? If the answer is yes, then fine-tuning is not the answer. Use RAG, bring the documents to your model. Don't train your model to inject new knowledge. Question number 3, do I need specific form of behavior consistently across thousands of requests at low latency and low cost? Then fine-tuning makes sense. Let's say your use case is valid. Now, what do you need? First myth to kill. You do not need a cluster of A100 GPUs. A free Google Colab is enough to start. How? QLoRA. Fine-tuning means retraining every parameter of the model. For a 7 to 8 billion parameter models, that's weights, gradients, optimizer states, 80 plus gigabytes of VRAM. Impossible on a home GPU. Here's what LoRa does instead. It freezes the model and attaches small adapters layer on top. Only those get trained. Less than 1% of the total parameters of the base model. And the Q means quantization. The model gets loaded compressed to 4-bit, roughly 4 times less memory. The result? An 8 to 12 billion parameter model can easily be trained on a 16 GB GPU. Even Colab's free T4 GPU works. You just need some patience. For tooling, I use Unsloth. Same training, roughly double the speed, way less memory, and it kills the boilerplate. They have ready-made Colab notebooks also. Take your model, plug in your data, and just hit run. One unpopular opinion on model selection, go small. The 3 to 12 billion range, because on a focused task, an 8 billion parameter model can beat a 70 billion parameter model easily, and it runs 10 times cheaper in production. A specialized beats a generalist in their own field. Now the sections that sounds the most boring and is the most important. People think fine-tuning is about GPUs and hyperparameters. The truth, 80% of the work is data. Right now, I'm building a dataset for a medical billing project, and I promise you, more time has gone on the cleaning of the data than training that data. And that's normal. That is the job. What does the format look like? instruction response pairs, basically example conversations. On the user side, the task and the input. On the assistant side, the exact output you want in your production. Same format, same structure. The model learns the patterns from these examples. Whatever format you feeds it in here, later it will spit out as the output. 3 rules. Screenshot time. Rule number 1. 500 to 1000 clean diverse examples beat a 50,000 rows of complete garbage. The model learns your data's mistakes too. Inconsistent format in your data, inconsistent model. Wrong answers in your data, congratulations. You have made a very confident wrong model. Rule number 2. If all your examples look the same, the model memorizes the narrow pattern of the data and it breaks down when you introduce a new input. Add edge cases, add hard examples, add the cases where the correct answer is I don't know. Rule number 3. At the start, pull 10 to 15% of your original data and lock it away. That's your evaluation set. The model never sees it during training. You'll understand why in a few minutes. This is the single most thing that stops you from lying to yourself. Where does the data come from? It's 3 sources. Real usage data, if you have it. Manual curation, yes. You sit down and create your examples by hand. Welcome to machine learning. And synthetic data, created by a bigger model. That's fine, everyone does it. But verify every single synthetic examples. Otherwise, you're transferring the mistakes of the bigger model to the smaller model. Now, training. Good news is, if you have done the previous steps correctly, this is the most easiest part. The whole process is just 5 lines. Load the model in 4-bit, attach the LoRA adapters, format your data with the chat template, run the training, save the adapter. It's all pre-written in the Unsloth notebook. Now, in Unsloth, there are thousands of settings, but 3 of them matters the most. Number 1, LoRa rank. Think of it as adapter's capacity. You can start at 16. Higher rank means more learning capacity, but also more overfitting risk. Somewhere between 8 and 32 covers 90% of the use cases. Number 2, learning rate. The default learning rate in Unsloth is the standard starting point in QLoRA. Don't mess with it in your first run. And number 3, epochs. How many times the model actually sees your dataset? The standard is 1 to 3. That's it. Past 3, the model isn't learning, it's memorizing. And one thing I want you to tattoo somewhere. Training loss going down is not success. The loss only tells you that the model is learning to mimic your data. Whether it became useful, that graph will never tell you. The evaluation set will, which is exactly where we are headed. One practical gotcha before we move on. The chat template. Whatever template you used during the training phase of the model, use exactly the same template in your inference. This tiny mismatch silently wrecks the model, and beginners lose hours in debugging. Time to finish the story from the start of the video. I was working on a US legal documents project. Fine-tuning the model, the loss curve was beautiful, the sample outputs looked professional. I was feeling very good about myself. Then I built a side-by-side eval. Same test documents, 2 different models. My fine-tuned model and the base model with a strong prompt. The results? The base model won clearly. 3 weeks of work, beaten by a well-written prompt. There are 2 lessons in this. Lesson number 1, your real competition is actually the base model plus a well-written prompt. Fine-tuning is only justified when it beats the baseline. So, build the baseline first, train later. Lesson number 2. If I hadn't built the eval set, then I would have shipped the weaker model in production confidently. The output looks good is not engineering, it's self-deception. Shipping models on vibes is like shipping code without testing it. So, how do you build an eval set? The answer is simple. Take your held out test set, the 10 to 20% we remove from the training data. Write down the definition of success, which output passes, which fails. Best case, a task where the answer can be verified. The code ran or it didn't. The numbers matched or it didn't. The right codes came out or they didn't. Then run both the models and compare the numbers. Numbers. not feelings. And if your task is verifiable with deterministic grounds, there's a level beyond this. Reinforcement learning with verifiable rewards, methods like GRPO. There, the model learns with the rewards itself. But that's a whole separate video. Tell me in the comments if you want it. Before we wrap up, 5 mistakes that I don't want you to catch. So, speed run. Number 1, fine-tuning knowledge into the model. No, don't do that. Use RAG. Number 2, skipping the baseline. Test the base model with a well-written prompt first. Then you can train it later. Number 3, dirty data. Duplicates, inconsistent formats. The model learns whatever you show it. Number 4, training on your test set, even accidentally. That's like seeing the exam paper before the exam. You get the score, not the ability. And number 5, more training more than 3 epochs because the loss was still going down. No, you don't have to do that. After 3, in most of the cases, the model starts memorizing, it stops learning. Recap in 3 lines. Fine-tuning teaches behavior, not knowledge. The data is the model. The GPU just compiles it. And until you have built an event, you don't have a model. You have a hope. In the next video, I am doing all this live. Actual dataset, actual training run, actual eval numbers on Colab step by step. Subscribe if you don't want to miss it. And tell me one thing in the comments. What niche would you fine-tune your model for? The most interesting idea might become my next project. See you in the next one.